So let's talk about ROC curves. I say the word ROC probably at least once every day. Okay, so ROC curves started during World War II. They're for analyzing radar signals. And the question that they answer is, for a particular false positive rate, what is the corresponding true positive rate? So just to remind you, the false positive rate is the number of negatives that are classified by the algorithm as being positive, then that divided by the total number of negatives. And the true positive rate is the total number of positives that were classified by the machine learning algorithm as positive, divided by the total number of positives. And so we want to have for each possible false positive rate, we want to have a corresponding true positive rate. Okay, so let's say that our classifier has a decision boundary that is right here. And the positives are over on this side and the negatives are over here. Then the true positive rate uses the number of positives classified as positives, so 1, 2, 3, 4, 5, 6, 7, and then divided by the total number of positives, which is here. So 7 on this side, 8, 9, 10, 11. Okay, so 7 out of 11. And then the false positive rate uses the number of negatives classified as positives, so 1, 2, 3, divided by the total number of negatives. So 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 3 out of 12. But what if I chose the decision boundary to be a little bit different? So what if I had chosen f of x equals 3 to be my decision boundary? Then the boundary might be over here. Like that. Then what happened to the true positive rate and false positive rate? Well, now we only have 3 out of our 11 positives classified correctly, and we have 2 negatives now that are classified as positives out of the 12. And let's put the decision boundary over here. And again, you can get values for the true positive rate and false positive rate. Okay, this game is kind of fun. So now, what if you sweep this thing down from top to bottom? Okay, just take the thing and just go like that and just sweep it all the way down. And every time you move this line, you record the true positive rate and the false positive rate. And then you plot all of those true positive rates and false positive rates on a scatter plot. And that is an ROC curve. So let us do it. Okay, so as you swing that line across, as you sweep the thing down, the true positive rate grows because we have more positives that are classified as positive. But also the number of false positives grow too, because now we have more negatives being classified as positive. So the curve ends up looking something like that. Now, the quality measure people use is the area under the curve, the AUC, area under the curve, or area under the ROC curve, AUROC. So that is the quality measure we often use for predictive models. So that's why I say it every day, because we're always evaluating the quality of our methods. Now, that line is random guessing. So if you are not better than that line, you might want to turn your classifier upside down so that it predicts the opposite of what it's currently doing, because it's worse than random guessing, which means it could be better if you flipped it. So hopefully you'll get a curve that, like I showed you on the previous slide. And most of the time you don't get perfect. Like perfect would be just straight up and then over. Most of the time you won't get that. Most prediction problems are not that easy. So you'll get something actually kind of similar to what I showed you on the previous slide. All right, so just to summarize, we talked about a lot of evaluation measures for machine learning models. You can summarize what the model does by looking at the confusion matrix, looking at the accuracy or the misclassification error, or you can look at the precision recall and F1 score if you're doing information retrieval. And then you could look at ROC curves and the area under the ROC. Okay, so these are all the ways that we enumerate in the data science course and more.